Hi, this is Lucien, DH7LM, and welcome back to Ham Radio Soul. If you're like me, all you ever knew about SWR is that it has something to do with reflection and that it's bad. But what is it really, and how does it affect your ham radio station? Let's find out. So, what's SWR anyway? Well, you might already know that if your antenna isn't matched to the impedance of your transceiver, in ham radio that's 50 ohm, you'll have a mismatch and you'll get reflected power back. This is because on RF frequencies, the resistance that a certain load presents to your source, i.e. your transceiver, varies with frequency and is dependent on the frequency you're transmitting on. So if you have a transceiver with an impedance of 50 ohm and a coax with an impedance of 50 ohm, but your antenna at a certain frequency has a different impedance, let's say 150 ohm, then you'll have a mismatch. And then the antenna presents kind of like a resistor or reactance, as it's called on RF, and will reflect power back. So we have reflected power. But you might ask, what about standing waves? Doesn't SWR have something to do with standing waves? And this is indeed something that I never really understood either until I delved into it a bit. To understand what a standing wave is and what it does, let's look at this picture. So you see here the forward power indicated as the green arrow and the reflected power as the red arrow. So let's assume your whole energy gets transferred back to the transceiver, right? In other words, you have an infinite SWR. Perhaps you have a short on your coax or an epic mismatch to your antenna. So your whole power gets reflected back. What happens if you look at your signal, and this is obviously just for illustrating purposes, it's not a real signal, is that it gets transferred back. Now what happens is that these two signals interact with each other. So at certain points they add to each other, at other points they subtract from each other. So there's a phase shift going on as well because of the reflection. So because of this interaction, a new wave forms on your transmission line. You see it here. Again, this is just an illustration, it's not a real wave. So the thing is that this wave repeats at certain points in your feed line. That is, if you were to measure the voltage at a certain point on the feed line, it would be the same at this point. So it will repeat every full wavelength. That means that you have a standing wave on your line. So that's how the name standing wave comes about. Now let's look at a realistic picture. This is a standing wave that occurs at an SWR of 4:1. So what you see in the blue line is your forward power, and in the green line your reflected power. The white wave is your standing wave, which doesn't move actually on the line. So what describes the standing wave in this case is the ratio between the peak of the white standing wave and the minimum of the white standing wave. And the peak is at 4 and the minimum at 1, or at least it's the ratio. So that's why it's an SWR of 4:1. You see, and that's also why it's called a standing wave ratio or voltage standing wave ratio of 4:1. Here you see another illustration of this. In the first picture we have again an SWR of 4 to 1. In the second it's an SWR of 2 to 1. And in the third it's an SWR of 9 to 1. So you see that the ratio between the peak and the minimum is what defines the standing wave. And of course, if you have a standing wave of 1 to 1, there is no wave because the ratio between the peak and the minimum is 1. So there is no difference. Now we understand what a standing wave is and what the standing wave ratio is. One question you might ask yourself is, does a low SWR mean that you have a great antenna? The answer, unfortunately, is no. Because if you look at this picture, if you have your transceiver connected to a dummy load where all your precious RF energy just goes to waste and is transformed into heat, then you will measure a perfect SWR at your transceiver. I mean, that's the whole point of the dummy load, right? So we can say no. Another case would be this. You have an extremely lossy feed line that again turns all your RF energy into heat. Nothing reaches the antenna and still you'll have a great SWR, of course, because there's no power reflected because all the power is lost anyway on the feed line. So that's something to keep in mind. And this is true not only for the extreme case that your feed line is so lossy that it loses all the power, but for the normal case where you have a feed line that loses some power, because every feed line does, right? So the problem is that if you measure SWR at the transceiver end, you might see a better SWR than is actually the case where you to measure it at the antenna, because obviously there's less power reflected reaching the transceiver than is reflected at the antenna feed point because of the losses of the cable. So I found a neat little chart in the German antenna Bible, the Rothamme, that indicates precisely what differences you can expect between measuring SWR at the transceiver and at the antenna. So as you can see, if you have, for example, an SWR of 4 measured at the transceiver end and you have a line with 2 dB loss, then your real SWR is like off the charts at the antenna end. It's like 30 to 1 or something, right? So another example, if you have an SWR of 2 at the transceiver end and you have a line loss of 2 dB, you'll have an SWR of 4 to 1 at the antenna end. So that's really something to keep in mind, especially if you operate on higher frequencies or if you have a very long feed line. Still another case I like to mention is this. If you have an antenna that is somewhat lossy, maybe your feed line is connected to ground or something, or anyway there's lots of RF power getting lost somehow in the antenna system, then again you'll measure a great SWR, but you may not radiating any power because nothing reaches the antenna. So again, a great SWR isn't always a good thing. The next question that many people ask themselves is, what about tuners? Don't they solve the problem of SWR? Well, not so fast. If you look at this illustration, you have your transceiver, you have your matching unit, which is a better name for antenna tuner, and your matching unit is connected to the antenna. What happens is that you reduce SWR only on the feed line between the matching unit and the transceiver. What happens after the matching unit, you have no idea, and the matching unit won't affect this feed line anyway. It will stay exactly the same as before. So if you have a really high SWR between antenna and matching unit, the matching unit won't do anything. The only thing this does is to make the transceiver believe you have a great SWR. So that's something to keep in mind. It really does nothing else. Okay, so we talked a little about the different scenarios where SWR comes into play, but how bad is it really? What about losses? That's the million-dollar question. So let's look at some cases. First of all, let's assume you have a zero loss line, which of course doesn't exist in real life, but let's assume that for a moment. At an SWR of 2.3 to 1, you lose approximately 15 watts of power if you are sending with a 100 watt transceiver. So in other words, only 85 watts reach the antenna. 15 watts are then reflected back. What happens now is that these 15 watts get reflected back again at the transceiver end towards the antenna, which then adds to the 85 watts. So you have 97.7 watts out. And the same cycle repeats actually. So at the end, if you have a zero loss feed line, all the power will be radiated eventually, even though you have a higher SWR. So it doesn't make any difference. Now, there is some debate, I guess, whether that's really true and whether this power really adds to the signal or gets lost because it lags behind or something. There are different opinions out there. I think in the book Antenna Physics that was recently published by the ARRL, he makes the case that it really gets lost, so it doesn't really help with the signal. Anyway, let's look at a more realistic case where you have line loss. Let's say you have 30 meters of RG213 and you're operating on the 20 meter band. That means you'll have a line loss of 0.7 dB. And let's assume again you have an SWR of 2 to 3 to 1. So because of the line loss, only 85 watts power will reach the antenna to begin with. And of these 85 watts, some will be reflected. In this case, approximately 12.5 watts. So the same game begins again. Power is reflected, then reflected again, then reflected again. Only it diminishes each time it travels through the feed line because of the loss. But it gets worse. If the SWR is high, we have to deal with additional line loss. In other words, the line loss multiplies in case there is a standing wave. The literature explains it like this. Because of the standing wave, remember the picture with the standing wave and the ratio between the peak and the minimum, the current is higher in the feed line and therefore more of your signal gets turned into heat. Conversely, because the voltage is higher as well, because of the standing wave, there is more leakage and therefore more losses between the dielectricum and the braid of the coax cable. So that's what I read. In any event, the line loss will multiply. How much? Let's have a look. This chart I took from the ARRL antenna handbook, and it shows just how much additional line loss we'll have to deal with in the case of an SWR that is higher than 1 to 1. So what we can see, for example, if we have a line loss in dB when matched, that is the regular line loss of the coax we use, of let's say 3 dB, and we have an SWR of 2 to 1. Then we have to deal with an additional line loss of 0.3 to 0.4. So that's really minuscule, right? Again, there's some discussion about whether this chart is really accurate, and the formulas that this chart are based on are kind of rule of thumb formulas. So there's some debate, especially when it comes to very high SWR. But it's still fair enough, I guess, and you can get a feel about the additional line loss you have to deal with when dealing with a higher SWR. And to be honest, it's really not that much. Look up this chart or go to one of the online calculators that are available and play around a little. You'll see that really higher SWR doesn't make such a big difference. Let's look at some examples. So we have a line loss again of 0.7 dB for our 20 meter transceiver, and that means again 85 watts reach the antenna. Now, if we have an SWR of 2 to 1, this goes down to 81.5 watts. 3 to 1, it goes down to 77.2 watts. 4 to 1, it goes down to 72.8 watts. So in other words, you have a difference that is just over 10 watts compared to the SWR of 1 to 1, which means nobody will ever hear this difference on the air. And we're talking about the SWR of 4 to 1, right? So it's not that small. Maybe we worried a bit too much about SWR, don't you think? But let's look at more examples. Let's say we have a line loss of 2.4 dB, which is kind of bad. This means only 57 watts out of our 100 watts reach the antenna at an SWR of 1 to 1. So if we play the same game again, we see that for an SWR of 2 to 1, only 52.7 watts reach the antenna. For 3 to 1, only 46.5. And for an SWR of 6 to 1, it's 33.5 watts. Remember, for an SWR of 1 to 1, we talked about 57 watts, as opposed to 33 watts at an SWR of 6 to 1. And 6 to 1 is really horrible, right? 6 to 1 will send most hams screaming. But the difference between 1 to 1 and 6 to 1 in this case, and it's already a bad case because 2.4 decibels of line loss is really horrible to begin with. So even in that horrible case, SWR of 6 to 1, you're ending up with not even half the power compared to an SWR of 1 to 1. And to be honest, on the air, it's questionable whether anybody would notice a difference between these two cases. Because, as you know, you need 4 times the power to make a difference of 1 S unit at the receiving end. So half the power doesn't really make a big difference, and it's not even half, right? Even at an SWR of 6 to 1, so that's quite something. Again, maybe another reason why we shouldn't panic too much about this crazy thing called SWR. Now, what are the lessons from all of this? First lesson. SWR isn't nearly as bad as people think, most of the time. I mean, of course, if you have an extremely high SWR, then you're gonna have a problem. And I guess on very high frequencies, such as UHF, where you have to deal with very high line losses, a very high SWR wouldn't help either. But if you have an SWR of, let's say, 3 to 1 or even 4 to 1 on the band edges, you really don't have to worry, especially not on HF. It's really no big deal, right? So that's the first lesson. Second lesson, be careful with a very high SWR. Of course, your transceiver won't like it. If you have a very, very high SWR, it can be really bad for the electronics in your transceiver, even though that modern transceivers have a protection circuit that reduces the power once the SWR gets too high. But still, it's not a good idea. Besides, if your SWR really skyrockets, the losses will manifest. So there you have a problem. Third lesson. Measure SWR at the antenna point, not at the transceiver end. This is important, especially if you're installing a new antenna at your home QTH. Please do yourself a favor and measure it at the antenna point and find out what the situation really is like, because otherwise you can be easily misled and deceived. Fourth lesson. Your SWR should be only good at the resonant frequencies or the frequencies you want to operate on. Because as we've seen, if you connect your transceiver to a dummy load, obviously you'll have a great SWR across the spectrum, but that's not what we want. So if your SWR is too good on too many frequencies, you should check whether you have a problem with your feed line, whether the antenna is really effective, or maybe some power just gets lost. So this isn't a good sign. It's a good sign if your SWR goes way up once you reach the band end, right? Or maybe a little further, but you get the point. And last but not least, try resonant antennas. I think these are very effective, not necessarily because they magically increase your power or something, but they have a great radiation pattern that you can predict. You know, you can orient your dipole in a way that suits your operation style or your interests or your geography. So that's really cool. And if you operate on a resonant antenna, you will have a good grasp of what's going on with the SWR, right? So you can really analyze it and see whether there's a problem. Either your SWR is too high or it's too low, which means again that some power might be lost. So it's a really good idea, especially if you're a new ham, I think, to start with resonant antennas, which are dipoles, of course, and the like. So that would be my 5th lesson from all of this. So I hope you learned something today. I certainly learned a lot during the preparation for this video, and thanks for watching. And if you liked the video, please consider subscribing. See you next time. 73s. Bye bye.